Okay, I put you some homework to get a little bit used to those kind of things. They take a basis in two-dimensional space, not to work too long. Two vectors. I introduced a new basis. It's a rotation of the first basis. And you have a tensor represented by a matrix. And find the representation of this tensor in the if the rank of three possibilities. If the indexes were all below, mixed tensor one above. This will give you exactly to understand how the position changes the representation. Then you have another short example. You have a 3x3 matrix, so that the determinant defined by the Levi-Civita symbol coincide with the one defined inductively by the expansion of the first row. It's a very good example to get the feeling of the Levi-Civita, reducing it, etc. It is exactly gives you all the formulas in the right way. And wants to calculate a curl of a vector field, and then the divergence of the resulting field. And as I told you, then the two differentiation go one after the other, we have to get 0. And okay, that's for today. Thank you.
Okay, hello everybody. My name is Tzvi Skar. I'm in Jerusalem, Israel. I've been working with Yaakov for over 15 years. So let's go over the homework solutions from the last lecture. The first problem was to work in a two-dimensional space with a given basis, E1, E2, and to define a new basis. Actually, this is not the new basis as originally appeared in the homework because we didn't like the way that the answers came out the same for part A, B, and C. So it didn't really illustrate what we're trying to illustrate, so we chose a different change of basis. We have a tensor which is represented in the original basis by the matrix with components A, B, C, and D. And we want to find out how these components change with the change of basis in 3 separate cases where rank 0, 2, 1, 1, and 2, 0. The rank again means the first number tells you how many upper indices you have, and the second number tells how many lower indices you have. So to change basis, we learned in the lecture that you must use a matrix. To go from the prime basis to the unprime basis, you must use the matrix that has upper indices primed and lower indices not primed. So there'll be a sum over these indices, and the J will remain. The general rule is that an upper index represents the row of the matrix, and the lower index represents the column. It's not always true, we'll see at the end, but that's the general rule. To go from the old basis to the new basis, use the inverse matrix. So what is L? To go from the prime basis to the old basis, E1 is actually 1/2 of E2 prime. That gives us this column 0, 1/2. And E2 is E1 prime. That gives us a column 1, 0. And the inverse is easily computed. Now let's look at the first case where the original tensor is rank 0, 2, which means 2 lower indices. So in order to change the indices from unprime to prime, since they're lower indices, we need to multiply by the matrix which has upper indices unprimed, which is the R. We'll have to use R twice. Go through one calculation slowly and carefully, and because the rest are very similar. So let's say we want to compute the component T 1 prime 1 prime in the new basis. So we set I prime to 1 prime and J prime to 1 prime. So we have this sum where 1 prime and 1 prime are fixed, and we have a sum over I and J. If we write out all of the terms, you'll see that 1 prime is consistently on the bottom, but the upper indices of the R's and the lower indices on the T go through all the possibilities, 1, 1, 1, 1, 1, 2, 1, 2, etc. Now, because of the zeros in the matrices, a lot of these terms will be 0. In fact, the only one that survives in this calculation will be when we take R2, 1 prime, remember that means second row, first column of R, which means the number 1. We have it twice, times T2, 2, which is D. So this first component is D, that appears here. And the remaining calculations for 1 prime, 2 prime, etc. are exactly similar. You just change the lower indices appropriately to match the component that you're looking for. And you end up with T prime is this D, 2C, 2B, 4A. You don't see the influence of L at all because we didn't use L. R has some kind of multiplicative 2 factor, and that comes to expression here. In the rank 1, 1 case, by the way, this is the rank that we're used to when we multiply a matrix by a vector or a matrix by another matrix. So you have to have one component, one index up and one index down. So now we have to use 1 time L and 1 time R, since we have one upper and one lower index. The same matrices L and R. And let's do, for example, T1 prime, 2 prime, which means we have upper 1 prime here is fixed and the lower 2 prime is fixed, and we sum over I and J. So we're looking for an element of the first row of L. This is 1 prime, the first row of L and the second column of J. When will we have in the first row of L and the second column of J a non-zero entry? So we'll have a 1 and a 2, and that's because we use the second element and the first. So that means we have to take this row 2, column 1 element of T, which is C, and we end up with 2C. And you can go through all the calculations. They're exactly similar. And you end up with something different from the 0, 2 example. Here you have a mixed influence of L and R. You have a half term, you have a 2C because of the 2 and R. And in the last case where the tensor is ranked 2 zeros, you have 2 upper indices. You must use L twice to convert the indices. And let's do the last one, T 2 prime, 2 prime. So again, you have 2 prime, 2 prime in the upper position. Sum over I and J. So you need something from the second row of L. So you'll have 1/2 times itself times A, and you get A over 4. Here you see the influence of the 1/2. So in each case, you get a different answer. So the rank of the tensor is quite significant. Okay, let's go to problem number 2. This problem was to show that the expansion of the determinant, as we all learned in school, agrees with the definition that Yaakov gave last time using the Levi-Civita symbol. So if you want to expand over the first row, everyone knows how to do it. Let's expand over this row. So you take A11 times the minor, which is the determinant of this 2 by 2, minus, you have to remember the plus, minus, plus, the signs alternate, A12 times the minus of this 2 by 2 matrix, etc. Now open the parentheses, and each term orders so that the lower indices are 1, 2, and 3. For example, this term, write it A11, A32, A23. So all the lower indices are in the order 1, 2, 3. Now to check that this is exactly equal to this expression below, it's enough to check, it's enough to check the signs. For example, check the sign of the parity of the permutation of the upper indices. Term is 1, 2, 3, that's an even permutation. So the sign should be plus, and it is. 1, 3, 2 is an odd permutation because it involves one switch. If you switch 2 and 3, you get back to 1, 2, 3. So that's an odd permutation, and it has a minus. Here, 1 and 2 are switched. Again, an odd permutation with a minus, and so forth. For example, the last one, why is this a minus? You have to switch 3 times. You have to move the 1 over to here, and then the 3 has to move 2 places. need to switch 3 times, which is also odd. So the signs are all correct, and that proves that solves the problem. We expanded on this a little bit. Last time, Yaakov mentioned the theorem that determinant of the product is the product of the determinants. Now we'll see a nice proof of this. We generalize the definition of determinant. In the lecture, the definition was to use specifically the permutation 1, 2, 3 up to n, for which epsilon is 1, so you didn't see the epsilon there. And to use here 1 to n, but really you can use any permutation you want on the bottom, and then multiply by the plus or minus 1, depending on if the permutation is even or odd. You don't need, if you want to use any permutation you want to use, you can use, but sometimes this extra epsilon pops up, as we'll see in the proof. So it's good to know how to handle it. So let's say we have 2 matrices A, B. Their product is C. Let's compute the determinant of C. So by the definition from last time, we can pick a permutation 1 through n, multiply by the Levi-Civita symbol. This gives us the determinant. Now for each C is computed as the product of a row of A and a column of B. So substitute for each C the product A, B, that corresponds to it. Now group all the A's together and all the B's together. Now we'll use the extended definition of determinant. Here I have a product of the A's times an epsilon, and the indices are the I's, which match the upper indices here. So that means that this whole expression is exactly the epsilon symbol with the K indices times determinant of A. That's the use of this definition here. And now I have the epsilon symbol with the B's, the K's match the K's up here, and I have 1, 2 through n. So that's exactly determinant of B. And this proves the theorem. Now we can go even a little further. We can go even a little further and compute the inverse of a matrix. We define the MKLs to be -1 to the K plus L power times the determinant of the corresponding minor. So let's see exactly what it means to expand the determinant of A along a particular row. Let's take the first row. We know this is the determinant. This is the definition. Since the sequence 1, 2 through n, where will I have A1, 1 in such a sum? Only when I1 is 1. So I pull him outside, and I'm left with epsilon 1 and the rest of the terms. Now I continue along the row, and I'm looking for A1, 2. So I can pull the A1, 2 outside when I2 is 1. And I continue going, and finally I pull out the A1n term, and I have another permutation of the indices here, and the 1 is at the end, times the remaining terms in the product. Now each one of these terms in the sum is an A11 times the minor, times the determinant of the minor. This is exactly a determinant of an n-1 by n-1 matrix. It has n-1 terms, it has the epsilon. And even though I have all pluses in the sum, these epsilons will alternate plus and minus, because in the second term, when the I moves to the second position, that will flip the parity, and you'll get a minus. The minus I've already incorporated into the definition of MKL, so I can write here plus. So I end up with expansion along the first row means you add up A1K, MK1. We know one can compute the determinant by expanding along any row or any column. So expansion along any particular row or column can be written in general in this way. And we claim that if J and L are equal, you'll get exactly the determinant of A. And if they're not equal, you get 0. Why is that? If J equals L, as in the example 1 and 1, this corresponds exactly to expanding the determinant along the jth row. If J is not equal to L, and you still use these minors, now you're using the wrong row. You're using the minors, which are created by removing the Lth row, but you're not using the right coefficients. In fact, you're using the coefficients which come from a different row. So what are you doing? It's as if you're computing the determinant of a matrix that has 2 equal rows. So that determinant is 0. It's quite a subtle argument. You have to think about it for a while. But this will be 0. So this proves the claim. If you divide both sides by determinant of A, you'll get this expression. So you have some kind of matrix here, 1 over determinant times this matrix gives you the identity. So that means that this is exactly the inverse of A. The little a's come from big A, so the inverse is exactly 1 over the determinant times this particular minor. Now from here you can get in one line Kramer's rule. You have a system of linear equations, AX equals B. So X is A inverse B. You can compute it directly. The kth component will be A inverse KL times the BL. Here's the sum is over L. Put in the expression for the inverse that we just computed. And you'll have now a sum MKL BL, which is exactly the expression of expanding a determinant along the kth column, but using the b's as coefficients instead of the entries of the matrix, of the original matrix A. So in other words, this is exactly Kramer's rule. The determinant of the matrix you get by replacing the kth column by B over the determinant of A. A very nice one-line proof of Kramer's rule. Okay, and the last problem was to calculate the curl of this covector field and then the divergence. So the vector field, this is a covector field with lower indices. When you take the curl, you'll get an upper index. So really the expression here means the ith component of the curl because the sum is over J and K and you'll be left with one upper index I. So for example, when I is 1, for epsilon to be non-zero, you have to have for J and K either 2 and 3 or 3 and 2. So here you have 3 and 2 and 2 and 3. And again, this means differentiate the third component of F by the second variable. So you differentiate this expression by Y and you'll get minus x squared. And then you differentiate the second component by Z and you'll get minus 2xz, but where there's a minus, so it becomes plus 2xz. And you do the same for the other components, and you end up with a vector G, which has upper indices. The divergence is a contraction on the upper index and the lower index differentiating. I mean, you differentiate the first component by X, the second component by Y, the third component by Z, and add them all up. And here you get minus 2x plus 2z, et cetera, and in the end, everything cancels out and you get 0, as it should be because we know divergence of a curl is 0.